Getting a major mining project permitted on National Forest System lands is like a chess game. It involves a lot of planning and strategy. It can take a lot of time, and you have to be persistent and innovative. Just as there are many different pieces on a chessboard, there are many different players in permitting a mine: the public, the mining company, the Forest Service, several state agencies, and so forth. Maybe the best way to describe the process is to use a real-life example. This is the Stillwater Platinum Mine near Columbus, Montana. It's a good example to use because it's just going into production and contains all the elements that are typical in establishing large-scale mining operations. Although the minerals here are platinum and palladium, the processes are about the same for most silver, gold, chrome, lead, zinc, copper, or other metal mines. There are 5 major aspects to all mine permitting: the legal aspects, the resource, the plan of operations, the EIS and decision, and construction, production, and reclamation. Just as the first requirement in playing chess is to know the rules, you must know the rules and laws that apply to mining before you can permit a mine. Metal mines on Forest Service System lands in the West are claimed under the 1872 mining law, which was passed to promote mining development on public lands with little or no restrictions. Through the years, primarily because of increasing competition for use of the public lands, that law was modified and other laws passed which constrained and regulated the miner. The first significant such law was the 1897 Organic Act, which recognized miners' rights to prospect, stake claims, and develop mines, but required them to follow 4 sections. Other laws were passed in 1920, 1947, and 1955, which removed certain categories of minerals from mining claim location under the 1872 Act, and gave the federal agencies more authority to manage public lands that were under mining claim. Because of an increased public perception that the public lands were being abused in the late 60s and early 70s, Congress passed several environmental laws which had a direct effect on mining, such as the 1969 National Environmental Policy Act, 1972 Federal Water Pollution Control Act amendments, and the 1973 Endangered Species Act, just to name a few. Passed similar legislation, which affected both public and private lands. A number of federal court decisions created case law which also influenced mine permitting. The Forest Service, relying on the authority of the 1897 Organic Act, which required approved plans of operation and bonds before mining activities could take place. Regulations 36 CFR 228 are the primary basis for the Forest Service's regulation of mining activities on National Forest Service System lands. Just as the board sets the boundaries for the chess game, the resource sets the boundaries for most of what follows: the mine location, its scale, and the economic, social, physical, and biological effects. Let's go back again to the Stillwater example. Platinum is a silvery-colored, rare metal used primarily in automobile catalytic converters and jewelry. It is supplied largely by miners in South Africa and the Soviet Union. The U.S. uses about half of the world's supply. Palladium is similar in appearance to platinum, but not as rare. It is used by the electronics industry in microcircuitry. Here, the rock containing platinum and palladium lies in a narrow, steeply dipping zone of the 3 to 5 mile thick rock formation known as the Stillwater Complex. The edge of this formation is exposed for about 25 miles along the north face of the Beartooth Mountains of south-central Montana. The complex has immense reserves of chrome, copper, nickel, platinum, and palladium. The area had experienced mining activity in the past, in the early 1900s for chrome, then again sporadically in the 20s and 30s. During World War II, chrome was mined in the complex for the war effort. Platinum was discovered in the complex in a 10 to 15 foot zone in the early 1970s. The Stillwater experience is typical of the cycle seen in many major mining areas. Discovery of minerals in the area many years ago was followed by a period of production and profits. An era of changed economic conditions led to mine closure, and then renewed interest, exploration, and development in the area will be followed by a period of new mining development and production. Many metal mines, such as the Stillwater, typically occur in scenic, mountainous terrain where there are many other sensitive resources and the potential for conflicts are high. Often, the same forces which created the metal deposits also created their beautiful mountain settings. In these mountain areas, space is frequently a problem. Where to find room to put the mine, mill, and tailings impoundment. Just as in chess, where a move by one player will require a response by the other, the submittal of a plan of operations requires a response by the Forest Service. The Stillwater Mining Company, or SMC, submitted their plan of operations in 1984. To give you an idea of the scale of their operations, they will mine 1,000 tons per day of ore, which will yield 80 ounces of platinum and 240 ounces of palladium. Over the life of the mine, about 8 million tons of tailings would be disposed of on the surface in the tailings impoundment behind an earthen dam. Large metal mines produce tailings. Tailings are generated from the milling process, processed through the mill to concentrate the valuable minerals. This concentrate is shipped to distant smelters to recover the metals. At the Stillwater, the mill concentrates the ore to 1/50th of its original volume. So, 1,000 tons per day of ore would produce less than 20 tons of concentrate to ship. In the mill, the ore is mixed with water and other chemicals, then crushed and ground into a fine, sand-like consistency by a large rotary crusher grinder called a sag mill and a ball mill. The ground rock and water slurry is pumped to flotation vats called cells. There, chemicals are added to the cells, and air is bubbled through the slurry. The air bubbles attract the mineral particles containing the metals and form a froth at the top of the cell. By skimming that froth off the cells and repeating the process several times, the valuable minerals are concentrated. The crushed rock residue from the mill is called tailings and is pumped to the tailings impoundment area. After it settles, some of the water will be recovered and reused in the mill. The bid with any mine is usually the tailings impoundment. The initial proposal for the one at the Stillwater was for a pond about 80 acres in size behind a dam which would be 160 feet high at the end of the projected mine life. The tailings dam would be built in 5 stages and would have 2 parts, the main dam and a toe dam. The toe dam would catch any sediment that erodes from the face of the main dam. The waste rock from the mine and from excavation of the pond area would be dams. After the pond in back of the first stage is filled, another lift would be added to the dam and more liner installed until 20 or 30 years from now, when it would cover about 80 acres. Large tailings, and therefore, require more room. At the same time of the filing of the plan of operations, Stillwater Mining Company also filed a lengthy, detailed baseline report, which described in detail the existing conditions around the mine of all resource values likely to be affected by mining. This, too, is common with most major mine proposals. Our response to the company's plan of operation is an environmental analysis and decision. SMC's filing of a plan of operations and baseline information started the analysis process required by the 1969 National Environmental Policy Act. Before we can approve a plan, we are required to make a determination whether the proposal may significantly affect the quality of the human environment. A number of state agencies are also commonly involved in this review. In the Montana Stillwater example, the Water Quality Bureau, the Hard Rock Bureau, and the Environmental Analysis Bureau all played prominent roles in the mine permitting. In fact, we decided to do a joint analysis with the State of Montana Environmental Analysis Bureau. We determined that there would be a significant effect, and this meant that an environmental impact statement would be required. Once an EIS is decided upon, there are a number of procedural steps required. The first would be to publish a notice in the Federal Register stating our intent to conduct an EIS. Then a scoping session would be held, where the public is invited to comment on the proposal and tell us what their concerns are. They may comment in writing or at public meetings which are held throughout the area. In the Stillwater case, we held a number of public meetings. We received 41 letters in addition to the people who commented at the meetings. A variety of concerns were expressed, but most related to water quality, social impacts, reclamation, recreation, wildlife, air quality, visual, and the physical stability of the mine and the tailings dam. These are fairly typical of concerns expressed on mine development anywhere. It was soon obvious that where to put the tailings impoundment was the biggest question. We conducted a tailings siting study in order to find the best sites. In fact, we found 18 areas that would have the capacity to hold the tailings. These 18 were pared down to the best 3 by applying criteria such as would the site violate any laws by impinging on wetlands or floodplains, or would there be major geologic stability problems, water problems, or require substantial costs that the environmental benefits of the site wouldn't outweigh. Once we identified the best 3 sites through this process, we developed alternative production systems, discussed the relative merits of each, and released all of this analysis in a joint Forest Service State of Montana Draft EIS in 1985. The Draft EIS, SMC did additional underground development and mine feasibility studies. The studies showed that a different mining method called cut-and-fill stoping would be most efficient. In this method, 60% of the tailings, the coarser fraction, the sand size, would be put back in the mine to control. The result was that less tailings, about 4 million tons, would be deposited on the surface. The mining company part-way through an EIS is also common and understandable. Because there are so many unknowns about buried mineral deposits, a company may have to modify its plans several times during development. This was all analyzed in the final EIS, and of the 3 sites considered, placing the tailings near the mine site was considered the preferred alternative. This was arrived at by using several selection criteria to respond to public issues and concerns. These included site suitability. Would the site have possible unstable ground or high groundwater? Impoundment spill control. Could any spill be contained before reaching a live stream? Tailings line rupture. The risk of rupture should be low. The longer the line, the higher the risk. Cost. The environmental costs must be worth the public benefit. Wildlife. Long-term impacts to wildlife must be minimized. Threatened and endangered wildlife. Effects must be reduced. Visual quality. Visual impacts must be minimized. The Custer National Forest supervisor issued a 16-page record of decision to approve the Stillwater Mine in December 1985, about 2 years after the initial proposal was submitted. Some EISs may take even longer than that. The decision listed 15 measures the company would be required to implement in addition to those already agreed to in their plan. Some of the measures included requirements to monitor and protect water quality and dam stability, measures to prevent subsidence of the ground over the mine, Submit a detailed engineering report with plans and specifications for the Forest Service to review and approve before construction started. Salvage all soils for later reclamation of the tailings and mine area. Monitor effects on wildlife and take measures to reduce effects on them. Bus employees to the mine site or require carpooling to reduce traffic on roads in the area. Visually screen the facilities as much as possible. The EIS disclosed that the impacts of the project were acceptable. The final aspect of the mine permitting includes construction, production, and reclamation. Most of what has gone on before has been on paper. In these phases, the real work begins. The mine openings, called portals, are needed to work the mine and will require access roads to them, and may require some facilities for mine ventilation and storage of materials. But the vast majority of the actual mining of rock in an underground mine is, obviously, underground. Since the ore must be mined where it is found, there is sometimes little latitude in where the mine openings can be placed, although there is usually some room for negotiation on the number of openings and their exact placement. The Stillwater Mine required 11 portals. Much of the waste rock generated in construction will be used on roads, in the dams, or put back in the mines. Protecting water quality is usually a major concern with any mine development, as it was with the Stillwater Mine. In some mine situations, the only way to protect water quality may be to line the tailings impoundment. Although neither the Forest Service nor the state required a liner, the Stillwater Company planned to construct and line the impoundment to reduce or eliminate chances for water contamination. They used a heavy plastic liner. This is sometimes done in areas where the subsoil is permeable and there are live streams close by. The laying of this liner typically involves excavation of the pond, laying of a sand blanket several inches thick to cover any sharp rocks, placing a carpet-like geotextile material over the sand to further protect the liner from sharp rocks, then laying the liner. A special welding process is used to attach the plastic sheets and ensure that the seams don't leak. The welder is a device similar to a hot glue gun. It lays a bead of hot melted plastic, then melts or welds the plastic sheets and bead together. The seams are tested and inspected in two ways. A vacuum machine is used to test every inch of the welded seam. If any bubbles are visible, the seam will be patched. The second testing involves cutting patches out of the welded liner seams and placing these test squares on a machine to detect how many pounds of pressure the seam can withstand. All testing is done by an independent laboratory. If any poor welds are found, the seam will be totally redone. The upper edge of the liner is usually tucked into a V-shaped trench and covered with dirt to anchor it. When another stage is added, the next series of liners will be simply welded onto the upper slopes of the Stage 1 liner. The 550,000 square foot liner cost SMC over $600,000 for material and installation. The total mine development costs were over $40 million. Other measures the company is implementing include installing piezometers in the tailings dam. These are devices which detect if the dams are becoming saturated and possibly unstable. The coarse material in the SMC dams should prevent any saturation, however. They have also installed 11 monitoring wells between the tailings pond and the river to detect any changes in water quality. Monitoring wells are essential to detect leakage from the tailings pond. If something harmful was detected, these wells could be pumped to remove the contaminants. After the tailings pond is full, the tailings will likely be reclaimed by dewatering them as much as possible, recontouring them, probably covering them with a geotextile and with a layer of soil, then planting grass and other vegetation. The Forest Service and the state of Montana required SMC to submit a reclamation bond of over $1 million. This will be held to ensure the mine area is reclaimed. The complexities of a chess game are not unlike permitting a mine. As in a chess game, you must know the rules and laws, know your resources, have a good plan of operations, and have a well-prepared response to it in an EIS and decision. Proper follow-through is a must to ensure that the construction, production, and reclamation phases result in a winning game.